I'll tell you just a little bit about the Science Gateways Community Institute, also known as the SGCI. So we're funded by the National Science Foundation to provide a variety of services to the Gateway community, not just National Science Foundation funded, but more broadly. And we provide them in three main areas. The first is support for building and running gateways, and that includes hands-on development support, which is a quarter-time person working on building your gateway. We also have consultants and also a catalog where you can promote your own gateway, but also use it to find other gateways or software components that you might be able to use in your gateway. And some of those software components are listed as affiliates of the Science Gateways Community Institute, which means that they are willing to help out projects who would like to use their software and help them with that integration process. So I do encourage you to check that out. Our second area of support is through education and training. Obviously, this webinar is one of those. We also have, oh, I forgot to update this. We have what were formerly called boot camps and is now called Focus Week, because it is a great opportunity to focus for a week on what it is that you're doing with your gateway. They are really wonderful, intensive, week-long introductions to how to make your gateway sustainable, promote it, find your audience, and so forth. We also have a variety of student-focused programs, which includes a hackathon coming up at PERC, the conference at the end of the month. If you have students who might want to be participating in a hackathon, do check out the registration form for that on our website. We also have an annual conference, which we have just opened registration for. That is running through the conference. Registration is available through till September 9th. And the conference is the end of September. And of course, we have a bunch of materials on our website. And then finally, we are an opportunity for you to network and be part of this community. We have a partner and affiliates program where we help point you in the direction of other resources beyond us that can help you. We, of course, have information on our website in the form of blogs and news and such. We also have a community forum that you can join, which is a Google group that lets you pose questions to the community. We put news announcements on there a bit too, but it's really a great way if you have a question about something technical or logistical or how do you guys do this. It's a great way to reach out to your peers and connect with them. And of course, our conference is also a networking opportunity. So those all three are provided by our various areas of the Institute. And I encourage you to visit our website to find out more about that. And then finally, I just want to put in a quick solicitation, question, begging, whatever, to ask you a favor of giving us a few seconds of feedback at the end of this webinar. We are funded by the NSF, and we'd like to be able to demonstrate to them that we provide something of service with their funding. This is really just two multiple choice questions, and then there's a third question that asks you whether you have suggestions for other topics, and we do look at those periodically and gather those ideas and design new webinar topics for it. So that I'm going to stop sharing and let our other presenters start sharing. And I'd like to introduce, and I'm totally excited about this, Jeffrey Sica and Bob Killen. They are both from the University of Michigan's division, which is called Advanced Research Computing. And what they do is provide support to all the folks on the University of Michigan campus who are doing stuff that's advanced, whether it's using clusters or Exceed or any number of other projects. And they are willing to talk about containers and Kubernetes, which I understand is something that they have talked about before. So I'm totally excited to learn about this now because it's not going to be scary. So take it away.
Thank you. Thank you. I want to emphasize, and I do this every time we only have like an hour, this is going to be a whirlwind tour. There is literally no way we could, give a true comprehensive overview of both containers as well as Kubernetes. We give a day-long Kubernetes tutorial that is still missing content. Like we could go for a week on it. Nothing is meant to be in depth here. It's really more of a primer so that at the end or throughout, people can ask questions and we can try and drive a dialogue towards what people are really interested in or curious about. So with that.
We sort of went through the intros already, but Hi, my name is Bob Killen. I'm a senior research cloud administrator here at the University of Michigan, ARC. I'm also a CNCF ambassador with a focus in academic outreach.
And my name is Jeffrey Sica. I am a senior research database administrator at ArcTS. I'm not sure what that actually means because I do a whole lot of different stuff that doesn't involve databases, like Kubernetes. So let's actually talk about, containers and Kubernetes. What is an application? What are containers and Kubernetes meant to help with? Well, to get into that, we have to understand what an application is. An application has code, and that code needs a place to execute with all of its dependencies. In many cases, that app may have some sort of like external backing data store, database, or some other service that it relies on outside of things, outside of the app itself. So a container is meant to package everything required to run that application and make it easy to distribute. It is a shipping container, but containers are meant to contain things, but many incorrectly believe that putting things in a container makes them more secure. That is a fallacy. You still need to build applications with security in mind. I will say that compromising a monolith application is a lot more damaging than compromising a single microservice. In that, microservice architecture can be more secure, but you still have to plan and architect accordingly for it. And you still need to think as an operator. The complexity of the application has shifted, but it has not gone away. Because a container is not a VM, you don't use the same tools to manage them. In this case, you have container runtimes. A container is not meant to be persistent. We tend to refer to them as ephemeral. Maybe you've heard of the phrase, treat your servers like cattle. You treat your containers just like that. You treat them as cattle. And like I said, the container is not secure by default. They do have some sane defaults, but if you really need to get into things like restricted data, there is a whole, it's a rabbit hole that we don't have time to go down. In a word, containers are flexible. They allow developers to build locally more easily. They can make testing easier, and then scaling becomes simpler when built right. Oftentimes in academia, scaling isn't actually one of the benefits because we're not really talking about things at Google scale. Typically, it's a researcher may have a single mobile app that's just ingesting data. Okay, they need 2 or 3 instances. You're not talking about scaling to hundreds, but the principles of building the application are the same. And another really interesting thing that people tend to not think about is many of these workloads can now span multiple languages and frameworks with entirely different teams being in charge of different, aspects or facets of the application. So you could have a, large research application where one team is working on part of it in Python and the other is working on it in Java. And as long as they're doing, basic API calls or some, language neutral way to communicate between them, it's kind of awesome, and you don't really have to worry about, all trying to package all of those different things into a single application. Containers are reproducible execution environments. They're easy to build and share, and it's trivial to connect the dots between containers and external services. That is why these things are taking off.
So now let's take a look at what is a container really. Put simply, they are a process with some additional properties and sort of voodoo magic that sort of makes them easier to manage. But in reality, they are definitely still just a process on the host. Containers are, isolated to a certain extent. They share the host. They share a kernel with the host, so they have some isolation mechanisms, but they are essentially just like a chroot jail sort of on steroids. They are very fast. And this is because they are simply just a process. They boot as if they were, you're starting a normal application. That is to say, unless it's Java, in which case, it might start a couple minutes later. But in general, they'll start pretty much instantly. They are immutable. And there's a little bit of a caveat on this, in that it's possible to not have immutable containers, but the way most systems and most groups treat them is that they are immutable. And this generally means that they cannot be modified. Once they are run, they are essentially like read-only. You can't modify them. So that you treat them as like cattle, not pets, sort of expanding on the analogy Jeff was using a second ago. So, and a container itself is actually not just a single thing. It's comprised of a whole slew of different components. And these are actually a set of abstractions built on top of multiple underlying system capabilities referred to as like namespaces. In FreeBSD, you do have something called jails, which are a single thing. But in Linux, a container is made up of a bunch of different. And these are all features of the Linux kernel, and they can actually sort of control how certain aspects of the kernel, or as the computer is essentially exposed to the process itself. And you don't actually need to like have in-depth knowledge of this stuff to use them, but it's useful to sort of like know some of the background information on this stuff. So if you do happen to see some of these like verbiage being used, you get an idea of like what they're referring to. The other thing is a container is a file system, and it's actually a hierarchical layer file system, which is essentially just like a bunch of different diffs that you can layer on top of each other to make like redistributing the different components of the application much easier, or different components of the container much easier. I really hate this slide, but it's still kind of an effective tool or effective image. With containers, there is no hypervisor overhead. You don't pay the performance price or the boot price, but you don't necessarily have the isolation boundary that they provide. And there are some container runtimes down that sort of blur the line, like Amazon's Firecracker, Kata containers. KubeVirt's kind of a funky one. But those are sort of out of scope for this, but I just want to like let you know there are some stuff out there that do sort of blur that line. So containers themselves are by no means a new concept. They sort of general idea have been around for a while. And it started with like chroot sort of back in the 80s. And it's honestly still used today by mostly like web hosting groups. And as you can sort of see, there's a large gap between chroot and BSD jails, but that was sort of the next iteration, along with like Solaris zones, and they're sort of like cousins to the current sort of what normal container. Later, we had a much smaller jump, going to Linux containers, where this really started adding the fundamentals of what we use today. And we saw this sort of really launch off in 2008 with LXC, and then in 2013 and 2014, we had like Google's "Let me containerize that for you," Docker, Rocket, and a slew of others. But they all sort of had like competing standards on images and different ways of like working with each other. And that became a huge pain point. And they all sort of got together and founded this thing called OCI, or the Open Container Initiative, which is essentially like a standard spec of what is a container, how do we run containers, and how do we glue them together. All right, with that, I accidentally muted myself when I was coughing. With that, a container actually has sort of three primary components. You have runtime, which is the thing that runs the handling of a container image, and the image is the next thing. An image is that sort of redistributable unit that you build and distribute. And then you sort of have the container itself, which is sort of an instance of the image created by the runtime. So if you think of it sort of like object-oriented programming, an image is the definition of an object, and a container is the instance of the object, sort of definition versus like execution. And really, when we start thinking containers, most people just immediately jump to like Docker. And Docker is honestly sort of the de facto standard of containers these days. There are many of other things available, and most of the other things out there are actually like compatible with Docker and use similar commands, just because like everyone knows Docker. There's certain advantages and disadvantages to others, but for the most part, like we're just going to focus on Docker, and that's all you really know about for now. But it was really built with like sort of the user and developer experience in mind, and it took the complex problem of gluing all those namespaces together and simplifying it into a like super easy way that made it like just sort of like take off. And it's sort of like I'd say the Kleenex of containers, where people sort of like equate them together. It also has some like very cute logos which help have it take off. All the concepts we've sort of discussed here, though, and are going to continue to discuss, are not necessarily like runtime specific. Let's see. So,
Question. Can you run a container or several containers on a VM? Bad idea. The answer to that is actually you do that already if you were trying to run containers or GKE or whatnot in a cloud. If you are doing any sort of container, running any kind of containers in a cloud, you're actually just running them in a VM. And that's actually one of the things that we do here as well. Any sort of, when you really think about it, and there are exceptions, but the generalization is anytime you're running a container in a cloud, you're actually running a container in a VM on a host. And in some cases, it's actually more like a container in a container inside a VM. And
it gets complicated. Either way, like most of the orchestration tools out there still deal with virtual machines. The cloud providers are still virtual machines, so we see it a little bit of everywhere, and it's very common to run multiple containers on the same host or on the same virtual machine. Okay. So sort of expanding, like when it comes to that whole like usability side and using Docker, really they just have like a couple basic commands that you like can use to just play around. Building the image, Docker build-t image name, running an image and mapping the port through. You can give it an explicit name, otherwise it's like a randomly generated one. If you want to see sort of the logs coming out of the container, you can do that. You can execute specific commands in there, remove them, or like remove an image. In general, the commands follow a very like good, common, like basic language structure that makes it really sort of like easy to use. That we're actually going to dive down into the fun part of container orchestration.
Yes. So you kind of have an idea of what a container is, why they have become such a widespread technology, but really all we've talked about is how to distribute or package your application, not actually how to run it in a meaningful way. To run containers in production, you need to have some generic fundamental building blocks that we're going to go over. In almost any instance, like you are going to have to address all of these bullet points to run an application in production as a container. So let's actually talk about Kubernetes because that's ultimately the de facto standard, much like Docker, when it comes to running containers in production. There is still Docker Swarm, that, however, is kind of waning, and there is still Mesos, and Mesos makes sense in certain specific situations, but at this point, Kubernetes and Kubernetes-based products is kind of the lion's share of the market.
One quick note on Mesos. You will generally see that if you're doing like Spark machine learning and a lot of the other frameworks that were built on it to begin with. It can also still scale larger than Kubernetes technically, but Kubernetes these days is definitely the lion's share of the market.
All right. So what does Kubernetes mean? It's one of the first questions that's always asked. It's Greek for pilot or helmsman of a ship, and a lot of the project tends to go around this whole Greek naval thing. Like there's Helm for packaging Kubernetes applications, and yeah. There's also the abbreviation of K, capital K, the number 8, and then S, which is K, then 8 letters, and then S. So there's your trivia of the day. The project was spun out of Google as an open source container orchestration platform back in 2014. And it was built from the lessons learned and the experiences of developing and running Google's Borg and Omega. Those are the big orchestration platforms in the background at Google. It was designed from the ground up as a loosely coupled collection of components centered around deploying and maintaining and scaling workloads. That is a huge mouthful, and we will actually explain what that means in a little bit. But what can Kubernetes really do? It can do a whole lot of stuff. However, everything requires some level of configuration. Some of this can be, configured to work out of the box. Some of it requires a little bit more investment of time and understanding how to make it work well within Kubernetes. One of the big things with Kubernetes is that it's declarative, not imperative. Another way of thinking about that is you call Domino's and you tell them you want 3 pepperoni pizzas delivered to your house. You don't have to tell them how to make the pizza or the directions to your house. You tell Kubernetes, I want this state, and it will continually try to drive towards that desired state. And one of the single biggest value adds Kubernetes can offer, and one of the reasons why it is such a big project and everyone is continuing to latch onto it, is no matter what you do in Kubernetes, you are using the same API regardless of where Kubernetes runs. If you are using Kubernetes on-prem, you're using the same API calls as if you were running Kubernetes in Azure or Google, you name it. You can run one or even more than one different container runtime in Kubernetes. So we are addressing the runtime problem with CRI. That is the Container Runtime Initiative. Thank you. I can never remember the last letter. Interface. Haha. So there is networking we have to address. We have that addressed with the container networking interface. Storage is kind of in a transition place. We're almost completely moved to this CSI, container storage interface, but a lot of people are still just doing things with raw volumes. With applications, you have to define how you want your container to run. In Kubernetes, there is this concept of a spec. Almost everything within Kubernetes has a concept of a spec, and it's the definition of what you expect from Kubernetes. Again, that declaration of what you want. Oftentimes you have scheduling rules. So if you are trying to run an application that requires a GPU, you need to be able to say this application needs to run specifically on nodes that have GPUs. There's a concept of affinity and anti-affinity within Kubernetes, so you can get very complex scheduling logic. And lastly, you want to know if your application is actually functioning and healthy. It's kind of important. So there is a concept of health checks in Kubernetes called liveness. I never know how to pronounce it. It's like kubectl. But there is a way where you can actually say, monitor my application and make sure it's running. And if it detects that it's not running, you have some control over what Kubernetes will attempt to do, whether it's try and restart something or kill it and then, or delete it and try and reinstantiate it.
So with that, I get to take back over and discuss some of the core concepts of Kubernetes. So these are essentially the core building blocks that make up sort of everything else that sort of exists in the Kubernetes ecosystem. And for practical purposes, we'll only cover a couple of these things, and that's like pods and services. But to give you sort of a greater idea, we have namespaces, which are sort of a logical partition of a cluster, where you can sort of carve up a cluster into smaller components. Think of it sort of like an allocation, or like a programming namespace in sort of more like application terms. So you can have different namespaces all running the same instance of the application. They can all be running side by side. No big deal. Labels actually allow you to sort of tag or annotate any Kubernetes object with sort of meaningful or actionable information, and then you can use those labels for all your different scheduling rules. So if you're like with like HT Condor, these are sort of similar to like class adds, and they go hand in hand with selectors. where you sort of define the rules on how you want to target those things. It's all the sort of like logical mappings on gluing things together. So a pod is sort of the atomic unit or smallest unit of work in Kubernetes. And a pod can actually make up one or more containers. And this is because, you might want to have a container that starts up and does some form of a network, like go and fetch some data. It's actually most commonly used with jobs and job schedulers and things like that to sort of like do like ETL type work or something like that. I want to go grab some data and then punch it off to the main container to sort of do the actual like actionable item. The other thing is like, you might have a container, what's referred to as like a sidecar that sort of functions as like a log shipper or metric shipper that knows a bit more information about the primary application that you're running or the primary container that you're running. And this sort of goes back to the container model of being very sort of pluggable and making it easy to link the different objects together through like ports or things like that. And then you can sort of glue them together into a pod, which is a better working unit that can make up the higher level things that have some of the other like complex scheduling information. Let's see. Going back to the sort of like logging example, some applications don't log to like standard out and standard error, but like speak syslog or have a lot of different log files. So a common pattern is to sort of like have that sidecar be like a syslog container, and so that will then ingest the data from the other container and then spit it out to like standard out, standard error, or send it off to like a remote location. Let's see. Pods are also ephemeral. Their IP, host name, everything about them is completely dynamic. You cannot use them for any sort of, a direct mapping for like any sort of like fault tolerance. That's up to sort of like higher level objects to actually manage that sort of aspect of it. And this is done because like, you never know what sort of network topology, what sort of, various things are going to be out there. So that's why the pods themselves are ephemeral. But you do have to have a way of accessing. Oh, sorry. It's all good. Yeah. So you still have the sort of like, you still have to have a way of getting to those pods and discovering them. So we have this other thing called services. And services are sort of the unified method of accessing the exposed workloads of pods. And I know that's quite a bit of a mouthful, but they are sort of the durable resource where pods are the non-durable or ephemeral resource. So a service is like a pointer. It sort of has a static cluster-wide IP address. Same thing, they are like namespaced and they all have a DNS name. And so because the service is static and the pods are ephemeral and it just functions as like a pointer, it doesn't matter like how many you have or where that pod lives. The service, you can still reference the service and still access it in a very easy, consumable way, without having to like do any sort of like service discovery or anything like that behind the scenes. The service itself acts as sort of like an internal mapping or a load balancer to your pods. So like you have 3 like web pods scheduled, you can create a service that like references those pods via those labels and selectors, and internally it will actually like load balance across the 3 of them. This can then sort of like expands out, even going to like the host level, where you have your pods spread across hosts, and you have sort of like it's known as a service type load balancer, where that will be like focus all the internal or external traffic into them and spread them across the hosts. I kind of said this already, but like these are the non-ephemeral or durable ways of accessing the pods.
So just going over things again, kind of bookending it. An application has code. The code needs a place to execute with all of its dependencies, and in many cases, the app may have some sort of external way of pointing to things. One of the things that we didn't touch on with services is there are many different types of services. Another different type of service within Kubernetes lets you point to external resources. So you could actually define a pointer, so it's something like dynamodb.mynamespace.cluster.local, and it will actually point to an AWS resource that you've defined. And then if for some reason you have to switch that out, you can do that just by changing the definition in Kubernetes rather than changing a bunch of config files within your application. So there are different ways of exposing things to Kubernetes and also different ways of exposing Kubernetes to your users. A container is one of the best ways to package code and dependencies in a way that many people can consume. Docker is the de facto standard because it is extremely easy to use and extremely easy to spin up and just get going. They have incredible documentation. Kubernetes is the forerunner for container orchestration, mainly because it is not only cloud agnostic, but it is just the best way to define a running container application. One of the things that we didn't touch on in this, but we need to shout out, is there is a project called MiniCube. If you are looking to work with Kubernetes, just learn it, spin it up and play. Kubernetes is typically I don't want to say bloated, but large type of an platform to spin up on your own. MiniCube lets you do it in a few keystrokes, and it's spinning up locally, and you can just play with it. You can destroy your own clusters, spin them up, not a problem. You can treat your clusters as cattle, which is actually now the new thing. We have quite a bit of reference material that we have both written ourselves as well as referenced other different things. These links will be available, and we are happy to not only go into these tutorials really quick and answer questions, but also just talk about what people's use cases are. We like to leave quite a bit of room at the end for talking and discussion because it's kind of boring just lecturing, and we really like hearing a two-way conversation. So
we do also have some demos and all that, but we figured we'd at least go to questions and try and tackle some questions and all that first before we dive into any sort of demos.
Yeah, because I could just pop open a terminal and go to town for like the next 20 minutes, but realistically, we're here for you, so we would love to hear any questions. Literally any question. Even if it's not necessarily related to Kubernetes, though that would be on topic.
Hi, this is Mona. I have a question about using containers to run a science gateway in production. Is that a good way to do it? I'm wondering about the reliability, the overhead and the security of doing that.
So that is a very common actually use case for it. Jupyter Hub is probably the most commonly used and most widely known sort of science gateway that is currently out there and frequently used. The Jupyter Hub people have actually released a sort of a Helm chart called Zero to Jupyter Hub. Helm is sort of the package manager for Kubernetes. So you can sort of just do Helm install Jupyter Hub and use their defaults, or you can highly customize its deployment. There are lots of ways of sort of extending it and customizing it to your specific use case. Another great project that actually packages much more for machine learning and things of that nature in there is called Kubeflow. And I would highly recommend taking a look at that as a good example. It also supports other things like natively running MPI jobs, and actually has a bunch of stuff built into it for running other complex jobs, as well as using your, what's the model library, or what's the thing called for that?
Is it CAF? No.
No.
I don't remember offhand.
No. Anyway, a thing that will sort of tie your results into and iterating over your results and saving the data for if you want to run different models and go back to different models.
Okay. One other thing that I wanted to touch on quick before I answer guest 16. I said we were going to expand on containers on VMs versus hardware. Yes, if you were running a container in the cloud, you are more than likely running a container on a VM. And no, that doesn't actually make sense because you are still having to do hypervisor stuff and you're not getting the performance benefits of just running containers. But what you are still getting is the benefit of being able to package things up in a meaningful way and distribute them fairly easily. But if performance matters, you absolutely should try running containers on bare metal. It's just most of the time no one can really do that.
There are groups that do, and most of the people that are actually more interested in like machine learning and running very intensive workloads, HPC style workloads, are definitely running it on bare metal. That's also because they have more bare metal experience and the tooling to manage it. In general, I should say the bare metal use case doesn't have as much sort of like documentation and stuff out there. That's mostly just because it's trivial for people to spin something up in a cloud provider. But if you take a look at like any of the sort of KubeCon or the Kubernetes conference type stuff, there's quite a few use cases out there with good information on how to deploy and manage this stuff on bare metal. One of the largest groups out there is Bloomberg, and they have some very good info out there on that.
All right, scrolling up. Guest 16, how to handle databases and file stores in conjunction with containers. I'm going to answer that in terms of Kubernetes. If you don't want it in a Kubernetes answer, I can give you a Docker Compose example. But for Kubernetes, if you were running a database, typically, let me start over. If you were running a database that is a single instance and you are not worried about fault tolerance or anything like that, you can just spin up what's called a deployment. A deployment is one of those higher level objects that we were talking about that manages pods. I want to say 50% of the time, if you were running a small application, running it as a deployment is just fine. People will probably not agree with me on that, but I'm talking practicality, not theory.
I don't agree with him on that.
So, the other way to run them is what's called a stateful set, which is the only way to run a stateful application within Kubernetes. But no matter what, you are still pointing a service towards a pod. Now, as far as file stores go, I'm not sure if you mean how do you handle persistent storage within Kubernetes or not.
We didn't cover mapping in data from the host, so do you want to expand on that quick?
Yeah. So there are 3 different ways you can map persistent data into a container. One of them is a volume. I kind of touched on that, but not really.
You should go down to just how you do it with Docker.
So in a Docker container, there is a concept of a volume, and a volume lets you mount data from a host into a container, and you can just pick a target directory and a source directory, and then it will map it from the host into the container. So that is at the Docker level. You can do something extremely similar with Kubernetes. It's called persistent volumes and persistent volume claims. This could be a talk in and of itself because persistent data is one of the more complex topics. But for the sake of speed, we'll just say that you can take host of a directory and then mount it into a container. But with Kubernetes, you can also do things like mount an NFS volume into a container or mount an S3 bucket into a container. You can do a lot of different things. That is the main way you mount persistent data into a container. In Kubernetes, I said there were 3. The next 2 are very similar. It's really just the definition that changes. One is a config map, which is small, concise data that affects how your application is running, not something that like a database hopefully that makes sense.
Config information.
Config
files.
Yeah. And then the second thing is what's called a secret, which is sensitive config information. So things like passwords that you may need at runtime. Let me scroll down and make sure. Okay. So to get back to it, how do you run a database and a file store in conjunction with containers? Typically, you are running a database either externally, and it doesn't matter, or internally, and you're dealing with container volumes. And then in Kubernetes specifically, you would create a service that points to your database pod, or database deployment, I should say. And then you would have your application point towards that service. We mentioned that every service gets an internal DNS name. That is precisely why. You can then pass that internal DNS name into your running application, and it will route to that database. If I could point the webcam more easily and legibly at the whiteboard, I would do so, but hopefully that gets the point across. If not, and this is one thing I want to make sure everyone understands, if you have Kubernetes or containers questions and you want us to talk at length about them, just ping us. This is one of our kind of job duties, is just spreading Kubernetes and container information throughout academia.
The introduction tutorials that we linked in the slides, and we'll send out the links, also goes over how to do this sort of thing.
All right, next question. I am giving all to you, Mr. Singularity User Group.
I have not personally used the Singularity plus Kubernetes, but they do have their own essentially containerizers that you can run with it. And they've been doing more with sort of what's known as like the Slurm operator. And this sort of expands on something we didn't cover. It's a much higher level Kubernetes thing, but it allows you to sort of create your own Kubernetes API. And it's called a custom resource definition. And they've created this thing where you can actually create a Slurm job within Kubernetes that goes off and runs in a Singularity container on an HPC cluster that's running Slurm.
One thing, Maestro, can you give me a quick example or expand on what kind of use case you're looking for? Because we could talk for the next 10 minutes about different use cases we see just in academia alone. And one question for you is, so we talked about OCI, the fact that you can have different container runtimes, but they all adhere to a standard. Kubernetes can use any OCI compliant container runtime. Is Singularity an OCI?
No, so they can use anything that is CRI compatible. If there is a container runtime interface, it doesn't matter if it's OCI compatible or not, it will be able to run and communicate with it.
Okay. No specifics, just so Maestro responded, no specifics, just as a way of differentiating a VM versus a container. So we gave the example of you have an application that's running a database. Typically how you would do that, depending on your scale and your use case, you might have the database running in the same VM as your application. And oftentimes you would be, if you're pushing your code to production, you might just be changing the code on that VM that happens to be running your application. In this case, in that case, it's kind of difficult to test everything because you have a single point of failure, and that's kind of scary. But also, it's really difficult to package up your application in that use case, as well as handle upgrades to libraries, just simple changes that you might want to keep things up to date. From a container standpoint, that's as simple as changing the definition of the container, spinning it up, and making sure it still runs, and doing some rudimentary tests. You can be as crazy as having unit tests and end-to-end tests and practical tests, but you can't really do a lot of that when you're just using a VM because it's really difficult to spin up a single VM and then run tests against it. I'm not saying it's not possible. We've been doing it for a while. But doing it with a container is so easy at this point that you can just do it on your laptop rather than your production environment.
It's a lot faster is the main thing. Pretty much anything, most of the stuff that you can do with a VM, you can do with a container. I'll say most. And with a container, it will be a heck of a lot faster getting up and going and doing all your testing.
All right. Next question. Any recommendations for getting relatively tech-green grad students and postdocs introduced to using containers and making the barriers to entry not seem too challenging? This is actually one of the things both he and I have been tasked with for our next annual period, was trying to present both more to undergrads and graduate students. Because the fact of the matter is, container technology now is, I don't want to say required, but definitely beneficial when you're trying to enter the job force, especially if you're going into any of the like big West Coast companies. They're all looking at people that have container experience, and this is kind of an area where education is lacking because it's so new and it changes constantly. So
one of the things that like sort of when you start going the container route, and it winds up forcing you to adopt a lot of other practices and a lot of other sort of thought processes. Thought process is the wrong word. Just like
programming paradigms.
yes, there we go. So you start thinking about doing all your stuff in a declarative way, and like building tests for everything, and sort of building everything in a pipeline so everything is easily testable and easily integratable with a slew of other things. And sort of these same things that have been great for the software industry have been great for science when it comes to reproducibility. The fact that if I'm running something, I can essentially pick it up, and if I have to like compile something crazily, I can produce this container that someone else can just pick up and run and not have to go through all that work. And if they want to rebuild and do all that themselves, they can use the sort of Docker file which defines all this stuff, and it makes it very easy for them to run it someplace else. In fact, we've actually seen a little bit of a growing practice of you will have a paper, something like that, and you will have your container image as well as like some sample data. And if someone wants to like test the reproducibility of the paper, they can take that sample data, pump it through the container, and see if you can get the same result.
I'm a little worried that we didn't actually answer Clifford's question. We have the two introduction tutorials that we wound up writing. Those are ours. Those are free to use. If you want us to come and present them, happily, just let us know. But also Kata Code has a lot of online tutorials that we haven't necessarily taken, but a lot of other people that we know have taken them, and it is very useful and entry level. So kind of pick your poison. You feel free to, again, use our presentations. Those are open source and meant to be looked at and used. Darren Boss asks, has there been any talk about getting some of the Internet 2 tier/TAP projects supported via Helm charts?
I talked with people at this last year at i2TechX. I don't know the status of it, but yes, there was talk of it.
Mona asks, does a container contain the OS or just application code? Let me pull up one example from my day job, because I can just pull this over really quick. So we are, sorry, hold on. Can you see this? I just want to make sure.
Right now we're seeing your PowerPoint or whatever it is you're using for displaying your slides, but we're not seeing your whole screen, I think.
Oh, okay. Sorry. I guess I can't do the whole screen. Can I?
You need to share.
You can. You just have to unshare and then, or stop sharing and then reshare your whole screen.
Boom. Does that look good?
Yeah, now I can see a big black screen with lots of code in it.
Let's change that. So
there we go.
This is kind of a crazy way, but a really good way to explain what a container actually would contain. We mentioned that a container has a hierarchical file system. Every single blue line is a layer in that file system, and you can reference other layers. So in this case, we are saying, let's use an existing container image, Python 3.7. The Alpine thing just means it's a smaller, different operating system that makes it a lot less, makes it smaller. Then we can define default environment variables and their definitions. We can actually run commands, and then the output of the command winds up being another layer. So in this case, we're saying, hey, do a quick update and then install all these different libraries. So we're not actually including the operating system code, but we're including a lot of different libraries and dependencies that our application needs to run, and everything else just gets inherited from the host operating system. And then you can, and then from here you can copy in specific code, or specific files, or actually entire folders and then point them to certain places. So in this case, we just want to copy in the requirements if you're familiar with Python. We want to install them, and then we want to copy in everything else. And the reason for that is we don't want to, copy in a whole folder if all we need to do is this, and for some reason this fails. It is a lot less intensive. There are a lot of tips and tricks when it comes to building containers and making them slimmer and leaner. But generally, you would just copy in the whole thing and then run pip install.
So the containers themselves will have the host's kernel, and then they can have essentially like the OS of, CentOS or Ubuntu or something like that. This specific example uses Alpine, which is a much sort of like lighter weight OS. You don't have to have a full-blown OS, and it won't have like the kernel components, but it will have the general user libraries and things like that that you're used to.
There is actually a cool thing is being able to distribute binaries, not just, like full-on applications that are, web apps, but say you're building just a Linux utility that requires 2 libraries. You can package that up as a container and then ship it with your 2 libraries, and then there's just the binary. And then it's a container image that's only, 15 megs, but still gives, users the isolation of running it as a container. So it's completely namespaced. You can specify what kernel permissions it has. Now we're getting into kind of the details and the craziness that you can do with containers.
The orchestration tooling that you commonly use for everything can be used for the smallest application to very large complex applications. So you're only sort of like learning and having to manage this sort of one group of rules, one group of logic for deploying and managing things.
Any other questions? This is the fun stuff that I like doing. I just like talking about it.
I was going to type, but I'll just ask it. Is it possible to actually get the stuff out of the container and say back into a VM?
So the container itself runs on a virtual machine, or can run on a virtual machine, and you can use the commands to copy files and things like that outside of the container. And the container image itself is actually just a tarball. So you can sort of flatten the layers down into a single tarball and then extract the entire tarball, and you'll see just like a directory of everything.
Okay, and if I could take a minute to kind of explain my specific use case. I'm new to containers, so I'm not quite sure if this is a good new use case, but I have a science gateway that the framework has a lot of sort of permission issues that needs an administrator of the VM to be able to set up properly. And I was thinking that perhaps we should put the Science Gateway framework into a container, and was wondering if that will, there were Tomcache issues, there was directory issues, and I was wondering if that will sort of isolate the framework in a way that we can then share with others and try to avoid the same kind of headache. And then if they would then basically make their changes or their customization in the container as well, and then just run the container on a VM once it's all done. Does that sound like a good
That is a very, very common use case. With the one thing is you generally don't want to make any sort of changes in the container itself. You want to, like any config files, anything like that, you're going to do sort of like on the host and pass those things directly into the container.
Okay, and I guess maybe then this may be the reason why I was thinking about actually getting stuff out of the container, because the customization is not only config files, but it could actually mean customizing the code for their use case as well. So,
depending on the code, you might still be able to pass that sort of thing in. Otherwise, what you can do is sort of have, you can sort of create like a base container that contains all your stuff, and then they can sort of like fork and create, much like Jeff is referencing the Python 3.7 thing here, you could have, from my Science Gateway, and then they can build off and do whatever they want from there.
And one of the things that you can do is Whoop. Okay, this is weird. One of the other things that you can do is actually, like, it shows I'm running commands in there. I'm even creating directories. You can also do things like chmod or chown folders as part of your, modifying an existing container.
Okay, thank you. It sounds like it's doable, but perhaps will require a bit of learning. Thank you.
Yeah, as weird as it is, almost everything is doable. It's just how deep into the weeds you need to go to actually figure out how to do it. And this is an instance where if you are up to like engaging us, we are happy to try and help you figure it out. We are very open to just collaborating and working with other people.
Okay.
They're in the CNCF, which is sort of the Cloud Native Computing Foundation, sort of the governing entity for a lot of these projects, including Kubernetes. There's an academia channel and an academia mailing list. And it's sort of just, the Slack channel itself is sort of quiet, but a lot of the people that are working on the same stuff are in there that you can bounce questions off of.
Okay, thank you very much.
Any other questions? Otherwise, I think we are getting close to time.
I will share my screen about next week's or next month's webinar if it's safe to do so. Did you have more, or you have other slides you'd like to share?
No, I was just looking for if we had the CNCF Slack in one of our other slides. And to answer your question, John, quick, I'm using VS Code. One more. Any quick impressions of using Kubernetes on commercial clouds, GKC versus Azure? I can rate them as GKE, then Azure, and then AWS. That is changing, but I mean, Kubernetes came out of Google. It's going to have the best support, and they also tend to have the best model for distributing Kubernetes. And Azure Kubernetes services, you go.
GKE is hand over fist the best one out there. Amazon is probably better than Azure these days. Most people on Amazon actually use a third-party tool to install and manage instead of their managed service. And Azure still is good, but they still have problems.
Yeah, whenever you're doing Kubernetes on AWS, you're using this thing called EKSCTL, which kind of takes away all the problems that Amazon's managed Kubernetes service has, and then just makes it easy for you. But GKE.